having AI on board for aircraft. So the title is Simulation Qualification for Safety Critical AI-based Systems. And I would like to start briefly, very briefly, the basic concept. Right, this is a Safe AI conference. I believe most of us are quite fit in many basic terms, but just to keep it complete. So we have the risk, and risk ends up with a hazard. When we have a ship there, the hazard is a tear on the deck, and to mitigate, to prevent the hazard, we mitigate the risk, and we can really paint the iceberg to make it a bit more visible for the ship. So if we have a software that does this mitigation for us, like if you have a software that shows us where the iceberg is, in which depth the iceberg is, and this software is a safety critical software. So this this prevents a hazard, right? So when it's a software, we know that we come up with a development assurance or design assurance, mostly called. It's basically building confidence in the process rather than the product. It identifies and removes the errors before the product is delivered. So the thing that identifies and removes the errors is the process itself, right? This is the approach that we're using for safety critical software for some decades now. So we have functional safety standards, the software, the function that is carried out by the software that mitigates the risk. We call it a function that needs to be assured. Then we have the functional safety standards. They basically describe the required level of rigor on the developmental assurance on the process, right? Based on the failure condition, severity, and the probability. We'll come to that in a minute. And most of us, I'm sure, is aware of one or another functional safety standard from 262 from Atomique to DO178C from Airborne software. So we'll be mostly sticking to DO178C for this talk. So how does it work? So we, again, most of you maybe have seen this one. So we have the process and the activity descriptions in our standards for DO178 in our body. Then we have the objective tables, right? The objective tables really gives us what needs to be done. What is the description of this rigor, specification of this rigor to be done for different levels of software, A, B, C, D, with kinds of some designations like when it's solid circle, then it needs to be done independently. When it's free, then you can do it in your own. Then you have references to the body of your standard. What is the output, description of your output, and the configuration control effort that you need to put on it. But the idea is it describes the objectives for each level. But what is this level, right? Again, this is not a new concept, so we all know the concept. So we have the categories of the hazards. It can be a catastrophic hazard, which can end up with multiple fatalities, usually the loss of an aircraft. It can be a hazard with no safety effect, and in between you have the other levels. The correspondence of the category to the assurance level is not really linear, so you have the function design assurance level, then item design assurance level, then you have the architectural issues, then you can handle a bit the risk management, I would say, but let's keep it very simple. If you have a software, the error in the software causes a catastrophic failure, then you come up with the level A software. If you have a software that leads to a failure that creates a physical distress to the passengers or cabin crew, or possibly including injuries, then it's a level C software. So when we look at the current airborne software landscape, so we have flight control, engine control at level A, the maintenance software, the terrain avoidance in level C, and for example, the in-flight entertainment systems in level E. But today, this workshop is AI's workshop, right? So how can we make artificial intelligence safe? So what is coming to the future airborne software landscape, AI-based systems would be a part of the future airborne software landscape that we know from today, from the commitment of regulatory bodies like EASA on this subject, right? When we look at the EASA AI roadmap, we see here 2025, the first approval of AI-based system, and 2030, we have a single pilot jet operations, and 35, we're talking about autonomous jet operations. And in between, you have different milestones with different levels. Level 1, we're talking about human assistance augmentation. With level 2, we start to talk about human-machine collaboration. And level 3 is basically the autonomous machine, right? So the roadmap is there, and the people are working on this roadmap. So when we look at this categorization again from EASA, so I used a lot of reference to EASA because the guidance is there, many documents are there, so that creates a good baseline to start the discussion. That doesn't need to be the formulation, but is the formulation to discuss today mostly referred formulation. So we have the AI-based system or subsystem that essentially has an AI ML component in it, AI component in it. The component has software items and hardware items, as well as this time an ML items or AI item. And AI item is a piece of software that has an inference model in it. So this is what we are expecting to have flying in the next decade in our aircraft. So here I would like to refer to one of the important studies that's being carried out. This is the concept of design assurance for neural networks. It's an innovative partnership contract between EASA and Daedalus. So it's hard to pronounce it, Daedalus, right? They are looking at basically the challenges posed by use of neural networks in aviation. So there are 2 reports that are currently being published, or partial reports, I would say, that are being openly published. They are very valuable in terms of the progress of the standardization. Or so the use case that they are using, so that I would like to convert to the topic, is a visual landing guidance system. So you have the camera on one side, capture the image, do the pre-processing, and then you have the CNN, and then you identify your what is it, the runway, and then you land, right? So in between you have the convolutional neural net. What is interesting here that they put on their report, that is the topic of this talk, is the synthesized data. So this is kind of a fact that we know, but this is now written on one of the important reports. The design and testing of safety critical machine learning models should rely on simulated and synthesized data, because this data is cost effective, because you can have this, acquire this data at a very low cost once the system is set up. So sooner or later, in one use case or another use case, one system or another system, we will start using synthetic images. So on the left-hand side, you see a real image. On the right-hand side, you have a synthetic image. These 2 images are, again, from Kodan report. One is from the real life. The other one is from, I think, one of the driving games. So and using these synthesized images is coming. So it's not, as I said, it's not kind of a wonder. So we all were thinking about it. So this is a paper that we published about a year ago in AIAA SciTech. In this paper, we were trying to look at how can we test really do the black box testing of the drop detection algorithms for autonomous air refueling. So we were using Viola, the CNNs, and we were then generating images to test the trained network. So, but the problem is we can do a lot in academic level, right? We can write papers, we can discuss a lot, but at the end, it needs to go to the regulatory authority, and they need to say, okay, you can use synthetic data for testing, and then you can fly your system. That is the decision that they need to make at some point. But How will they make it? So the references, we have two references again from the Codan report. One is the AI as a means of compliance for certification credit in simulated and rig testing, and the other one is for unmanned systems, again, work in progress report. In both of them, they say, provided the item to be evaluated is simulated with adequate level of representativity, you can use the simulated data. In the second one, they say simulation results can be used as long as the accuracy is justified. And simulation run coverage is justified. Approximate non-zero amount of physical testing is used to validate the simulation results. Anyhow, the current state of the art, the current view of the regulatory authorities seems to be converging to the fidelity. So they would like to be sure that the simulation fidelity is high enough to be used for testing, to be used in testing, not particularly for neural networks or AI systems, but testing. But still, we need to think about it. So how can we really qualify or quantify simulation fidelity? Is not an easy question. I know it from flight simulators domain. The people are really working in the last 40 years to come up with objective criteria for the simulation fidelity for a very well-known domain. So if you're really doing visual simulation and talk about fidelity, it's not very easy to quantify it. So I would like to come to the proposal that we also use design assurance approaches for simulations to come up with a required amount of confidence in our simulations, to use their output, like the synthesized images or simulated images for AI systems. So we know it, right? So from the all other software tools, however good the design or however accurate its implementation, the integrity of a system relies on its correct operation of tools used to create it. So tools are crucial. So if you have a tool that's making errors, that cannot create, detect bugs, you have a problem. So in AI-based systems that use simulated data for training or for testing, correctness of the simulation is a safety concern. This is one of the effects that I would like to share today, or not effects, but claims that I would like to share today. It's a bit strong here. And what I would like to say is, let's look at DO330 that we already have, software tool qualification considerations. That is an augmentation or a standard that augments DO178C, and that describes the tool qualification process that guarantees that the tool is developed and verified using adequate process in order to obtain a confidence in the tool's functionality. So it describes tool qualification levels from 1 to 5, 1 being the most rigorous one, 5 being the least rigorous one, and you have the different software levels. That's very important. How you where you use your tool. You can be using your tool for a DAL A system or a DAL B system that changes the importance of your tool, and then the description of how you use your tool. You can use your tool, the output of the tool is a part of your Airborne software, or you use your tool to for verification purposes, but you have another mean also to do the same verification. So this is the criteria 2, right? So in criteria 2, then you have a tool that you use for verification, and you don't have other means to do that verification. So based on the criteria, how you use your tool and where you use your tool, you land to a tool qualification level, and voila, it's the same approach that we have in the DO178. You have the objectives, and each objective apply to different qualification levels. Pretty much like the DO178, you have the references to the activities, the description of your output, and based on your tool qualification level, you ought to do or confirm number of objectives. How about we apply the same approach to simulation engineering? So there is a standard. It's called IEEE 1730. It's recommended practice for distributed simulation engineering and execution process. It's been done like in the last decade. This describes you a very kind of accepted simulation engineering process, starting from defining simulation environment objectives, over the conceptual analysis, simulation, design, development, integration and test, execution, and analysis and evaluation of the results. So simulation engineering is a bit of an extension of software engineering, or simulation is a software engineering process, because you start with the objectives, end up with the, using this software for simulation purpose. But anyhow, so this process is being used particularly in defense enterprise in all over the world, I would say, for military simulations, and here it can be a good baseline. Then what we need to do, we can come up with simulation qualification levels inspired from the O330, and then we can set up the objectives based on this discipline. What I have done is I just drafted kind of a proposal. If your simulation results or output of your simulation is used as a part of your system, it's a criteria 1. If you use your simulation output to test your system, it's 2 or 3. If you have no other means, it's 2. If you have another means, it's 3. But if we map this description to the AI-based system, so if you use your simulation to train your network, it's criteria 1. If you use it to test your network, then it's 2 or 3, based on if you use other real data or not. Then we have what I have done is come up with the objectives from the DSIP with the references in DSIP, and then try to identify the applicability to SQS with the outputs, again references to DSIP, and the control categories. The control categories objectives, we try to really align them with 330, and then use as much as possible this DSIP standard. Here's an example. For example, you're developing an AI-based system, autonomous air refueling. It's an assurance level 8. We can discuss it, but let's keep it like A for the moment. And then the simulation utilization is we use data generation for training for this autonomous air refueling. Then qualification criteria is 1, because the simulation output is a part of the system, thus can introduce an error to the system. Then the simulation qualification level is 1. An example objective is simulation conceptual model, according to section 422 in 1730 in this standard, need to be developed. And this conceptual model need to be verified independently that it represents the domain adequately. So this is a very simple use case that try to make it kind of like real in your eyes. So what I would like to say is future AI-based systems will rely on simulation, probably for both design and verification. And simulation fidelity itself is not adequate. Even if adequate, it's not an easy measure. So it's not really easy to put a fidelity stamp on a visual simulation that easily. And then we have a tool that we know how to use, and that's been working. This is development assurance or design assurance technique. We can apply it for engineering simulations for safety critical AI-based systems. And as I said, IEEE 1730 DSIP is a good starting point. So this is what I would like to discuss for today's presentation. So I think in 20 minutes, I try to make it happen. I hope that you could keep up with a bit of a pace here. So looking forward to have your questions and have a nice discussion in the next 10 minutes.
Thanks, Umut. I think we'll open the floor for questions. I think we have 10 minutes, right, Huáscar?
Right. Yeah, we have 10 minutes.
We can discuss a bit.
Yeah, maybe I have a question, Umut. Thank you very much for this nice presentation. I think it's very good overview of kind of issues and the directions to go in this. But I also think that this is really a more complex issue. So I have a couple of questions for you. The first one is regarding open source. So, you know, already in systems which are not AI based, open source is a problem for tool qualification. And now in deep learning tooling, so the trend is to use more open source. So what kind of issues that there could be regarding the fact that open source and open data in general could be a problem for tool qualification?
So I think tool qualification will be one of the big challenges in AI-based systems that we are seeing in this working group also. Or maybe not, because when you look at tool qualification, this is very important. If you verify the output of the tool, you don't need tool qualification.
Right.
So, for example, you don't need to care about qualifying TensorFlow because the output will be tested. So all open source tools that we use for modeling are actually does not require qualifications really, because the output will be a model and we will test the model and we will guarantee the model is correct. So that's why a part of the story is kind of good. But then comes the story about for example, optimizations. So if you have a qualified optimization tool for a specific target, then maybe it's useful to qualify it. Otherwise, you need to do all the tests you have on the target platform also. So open source is bringing also quite a huge problem to tool qualification. I have kind of a hope, I would say, with the new approach that is coming with this overarching properties. I don't know if you heard about it. So the FAA is pushing in, I wouldn't say a new kind, but let's say a new kind of certification that will enable us to put a bit more alternative approaches, I would say. And with overarching properties, one of the first papers came from Adacore. They showed how they can qualify their code generators with overarching properties, and it is very promising to apply it to open source software also. But I think we're at the very beginning, so it will be one of the topics we will be dealing in the next couple of years or maybe a decade even.
Hey, thank you. I have other question, but I will let it to the end if we have some time to let other people to ask.
John?
Yeah, thanks, Mauricio. It was very interesting. And I think as a matter of principle, it'd be really good if we have the same criteria to apply to simulators used for AI and machine learning parts of systems and conventional parts of systems. So building on this IEEE standard makes sense. But do you think there are extra things that we need to do for systems that make use of ML, or do you think we can simply use exactly the same criteria that already been established?
Yeah, I think so. This is not really looking at the system itself, right? So how do we certify the AI-based system is quite a discussion. I think we will have a very nice presentation in 10 minutes or 20 minutes from now that shows us what's going on in the working group. From the simulation perspective, so I'm putting myself in a seat from EASA or from FAA. So they will receive an application that uses a simulated data for training of the AI ML-based systems. And they will have the results that the simulated this training data, even with the simulated test data, working perfectly. So will they approve it? So how they will be sure that the simulated data represents the real world? How data? So this is the question that I'm asking. How can we approach this problem? If the people will, it seems that we will be using simulated data either for training or for testing. What would be the means of compliance then to show it? So this is my question that I'm trying to answer.
Beatrice, maybe you have a question?
Yeah, actually, I wanted to Thank you, Umut, for this very nice presentation. And maybe to highlight again, indeed, one of the important aspects of the simulated data for AI, because probably we need to use them to create these corner cases to make all the verification possible. So this brings to the adverse examples, and if we are able to create the good adversarial examples to test our systems of AI, this is perfect. And another point that I wanted to bring related to Huáscar question about open data, I think we should not forget, in general, in open databases, what we forget, and actually when we want to do real products, we very often remind this, is that open databases are very often already cleaned. So you cannot know what the real problems are from these databases. And actually, if you are not aware of all the perturbances and everything, then your systems are not designed as robust as you may want. So this is for the two aspects I wanted to bring.
True.
Thanks, Beatrice. Maybe a last question for me, Umut. Have you thought about maybe this argumentation approach to showing that the tool, satisfies a fidelity requirement, where actually you have to come up with evidence showing that your simulation, right? And it's a bit, divergence from the prescription of, telling, telling or prescribing a process for obtaining, let's say, a specific tool quality level.
So I was thinking, I was thinking how we can apply fidelity approach to the AI problem also. Like, so I spent almost 10 years for flight simulators at DLR. So we look at flight simulator fidelity a lot. That I have kind of an experience how the people are looking at the fidelity of a flight dynamics model against the real flight data. However, when it's an image, I'm still really clueless. So how can we really come up with a quantifiable tolerances that we say the image should diverge from the real image, or simulated image should diverge from real image with what? So only the pixel values, the luminance, I don't know. So how shall we really describe the tolerance? Because the fidelity really relies on the tolerance with the real data and the simulated data. When it's an image, so I'm clueless. Maybe there are some approaches, but I'm really searching for other fellows that's really good at computer vision. Maybe we'll come up with other solutions. So I'm more coming from software engineering and simulation area. So I'm really sticking to this design assurance, but looking forward to see other papers try to describe this fidelity problems. Because if it will be fidelity, somebody needs to say me, this is the fidelity metric, and this is how you can measure it.
Yeah. Thanks, Umut, again for a great presentation. I think we'll move on.